Hi. So in this lecture I want to pick up some problems that we have already done in assignments, right? Some previous problems, we want to pick them again. And we want to look at what was the time complexity of solutions that we have written. And in a lot of these cases, what would happen is that the code that you would have written earlier will not be like a really good solution. The time complexity will not be that good, and we'll try to improve those solutions. We'll try to see if there are better solutions which exist for those problems. Okay. So we'll start with a simple problem. Let's start with a problem that we have done I think both iteratively as recursively. So the problem is power. Let me change the color. Right. So power. Right. So to calculate power, that is x to the power n, I have two ways of doing this. One was iterative, in which what we can do is we can take I is equals to 1, I is equals to 0, answer is equals to 1, while I less than equal to n, right? While I is less than equal to n, I can do answer is equals to answer into x, and then that will, my answer will have the required output, and I have to do I is equals to I plus 1 as well, right? So something like this will work. Sure. So for example, if you want to take an example, if n is equals to 1, yes, if n is equals to 1, what's going to happen is you will have 0 less than equal to 1, so you will multiply x into answer, so answer will become x. Answer was initially 1 multiplication, it is x now. Because I is 1 now, we started with 0, because it is 1 now, 1 less than equal to 1 is true, we'll do one more multiplication. So there is a mistake in this code. I think now this should work, right? So this is the iterative solution. The recursive solution is very simple, something that we have done earlier. If n equal 0, return 1, right? X to the power 0 is 1, and otherwise we can return x into power of x comma n minus 1. So what are we saying? That recursion will find x to the power n minus 1 for me, and I will multiply it with x, and that will be my solution, right? So that's okay as well. So now for both these, what is the time complexity and space complexity? So if you look at time complexity for this one, should be straightforward. I hope you can do it. So if you look at time complexity here, we are doing some constant work. That's not important. The important part is this loop. This loop is going to run n times, right? If you want to find x to the power n, you are going to do n multiplication, and each time you are doing constant amount of work. So we are doing kn work, which means big O of n. So time complexity is big O of n. What about space complexity? So we are not using any extra space. We are just using couple of extra variables which does not count. So the space is constant. So for iterative, our time complexity is big O of n and space complexity is big O of 1. What about the recursive solution? The neat solution, the solution which is very simple in terms of the code, right? So if you look at the time complexity, so it's again very similar to factorial. In each function call, we are doing constant work, we are checking something, we are doing the multiplication. So power n is doing constant work, but it has to wait for power n minus 1, which has to make a call to power n minus 2, and so on up to 1 or up to 0. So there are n plus 1 function calls, and each function call does constant amount of work. Or you can say Tn is equals to some constant plus T of n minus 1. And we already know the time complexity in this case, recursive, is going to be big O of n. Even in case of recursion, if you solve this recurrence relation, you will get big O of n. What about the space complexity? Space complexity is interesting because it looks like we are not creating any extra variable, but in reality you already know the answer to this. You have so many functions. When you reach the base case, you will have all these functions waiting for you, which you have created, all the space that you have created. So big O of n space complexity as well. So if you have written any of these solutions in your previous power functions, then your time complexity is definitely big O of n. Space complexity in case of recursion is big O of n. In case of iterative, it is big O of 1. I think we can improve this a lot. I think we can improve the time complexity from big O of n to something else. That's what I want you to think about. How can we improve this solution? Right? Just to give you a hint, right now we have divided our work this way. Is there any other way to divide our work? Instead of doing this, can we divide it into some other components such that the work we need to do becomes far less? Okay, perfect. So give it a try and think about it, write the code and see if it actually works for you or not. Okay, thank you. Hi. So in the previous session, I discussed the time and space complexity of power. And I asked you guys to calculate power in a faster way. Some solution which is better than big O of n time complexity, right? So we already have a order 1 space complexity solution, which is the iterative solution. So we want to focus on the time complexity first. And in most of the problems, we will be more worried about time complexity rather than space complexity, to be honest. Time is a lot more important, the amount of memory that we require, right? Like if you are able to speed up things, then generally you will be okay giving away a little more memory to it, right? So as a rule of thumb, like generally we will basically give preference to time complexity. That being said, space complexity is also important. And if the question itself, or let's say you're sitting in an interview and the interviewer says you don't have extra space, then obviously you need to just make sure that you are not using extra space and you can use extra time if required. Okay, so it depends on problem to problem, but in general we will be talking more on time complexity. Okay, so we want to reduce this. Now I asked you to think, how can you divide this problem into some other component? I think one thing that I can do is something like this, right? We can do something like this: x raised to power n by 2 raised to power 2. Effectively, to make things a little more clear, you will have to say if n is even, then xn is equals to n by 2 into xn by 2. If n is odd, then let's do the integer division, right? This is the integer division. So n by 2 will not give me 0.5. So if n is 5, 5 by 2 will be 2, not 2.5. I'm assuming that. And then I can do another multiplication with x, right? Something like this. Now, why is this better? Why is this better? Let's see. So for now, let's just focus on this part. So that's something that you are trying to say, right? Now, let me just quickly write the code for this. Let's say you write your power function this way, right? If n equal 0, return 1, otherwise return. And for now, let's assume n is even. I don't want to complicate my code. So for now, I'm assuming n is even. Okay, let's not assume it. So I am saying we will take care of two cases. If n is even, we will do this. N is odd, we will do this. This is integer division into x, right? So in case of Python, which requires this to be double slash, even then I'm just saying like think of this as a double slash. So basically we are doing integer division. Okay. So if I have to write code for this, I'll write something like this. Comma n. If n equal 0, I will return 1. Otherwise, you can say if n percentage 2 equal 0, then I can return. So a lot of you are going to write code like this. And I'll tell you there is some problem with writing code this way. Else return x into power x comma n by 2 into power x comma n, right? So if you write your code this way, and it's just pseudocode, right? Like don't try to find whether I missed my semicolon or some other colon. Don't worry about too much about that, right? Like just let's just focus on the pseudocode. So the problem that I have with this code is that you wanted to get x to the power n by 2. So you called power function. You require x to the power n by 2 again, and you called power function again. Doesn't make sense, right? It's like saying within one line of code I require 5 factorial. So I'll call factorial function with 5 and then I'll again call factorial function with 5. Instead what I could have done is save the value of the return value of 5 factorial and use that twice. So if I don't do that, like I think like the clever way of doing it, the right way of doing it, if I write my code this way, what would be the time complexity? My time complexity will be Tn is equal to some constant work. That constant work may includes checking this condition, doing this multiplication. Even if I have to do this extra multiplication, that is also constant. So some constant work plus I need to call two functions of half size. So 2t n by 2. This will be the recurrence relation for this particular code. You try to work a little bit on this and you will see that this is big O of n. You are actually doing big O of n work. Okay, so your time complexity has not reduced from where we started. It could have been much better if I had here itself, if I do small power is equal to power x comma n by 2, and then instead of writing this 2 times, this function called 2 times, I could have written small power into small power. Same thing here, small power, small power. Now what you have done is, to solve a problem of size n, I'm doing some constant work, checking this condition, all of this, plus I am making only one call of n by 2 size, t n by Tn is equals to k plus Tn by 2. You should have seen this recurrence relation already while you were trying to find time complexity of binary search, right? This code is very similar to binary search in the sense that I am doing some constant work and then I am making a problem like a call on half-sized problem. That's exactly what binary search did. So it will have exactly the same time complexity and space complexity as binary search. So the time complexity will be big O of log n, which is much better than big O of n, and the space complexity will also be big O of log n, because you're calling n is calling n by 2, that is calling n by 4. So this way you will have maximum log n function calls. Okay, so we started with order n solution and we have reached order log n solution. Thank you. Hi. So in this session we want to pick up a new problem, and we want to see what is the time complexity of the solution that, so I would have thought for the first time, like if you give me that problem for the first time, the first solution I'll think of, I think most of you would have written the same solution. So let's find the time complexity for that solution, and then I would tell you a little hint using which you can think of improving the time complexity, and later on we will discuss what are the different solutions possible for that particular problem. Okay, perfect. So let's say I give you two arrays A and B, and I ask you to find its intersection. Right, given two arrays you need to find the intersection. So the way I would have done it, I would have picked the first element, searched in B. These are not sorted array, so I will have to do linear search. So I'll pick the first element, I'll do linear search in B. I'll pick the second element, I'll do linear search in B. Pick the third, do linear search, pick the fourth, do linear search. That's the most obvious solution that you can think of. I generally call it the brute force solution because you haven't really used your mind a lot. You have just basically, you're using the power of the computer to just get stuff done, right? Brute force. So if this array has m elements and this array has n elements, so the amount of work you will be doing will be, you will pick the first one, do n work, for the second one you will do n work, for the third one you will do n work. So basically you will be doing big O of mn work. This is the time complexity of the solution if this is what you have implemented. That pick every element of A and find it in B. Right? Space complexity is nothing because we are not creating any extra array. The only two arrays I am using are the ones that are part of input. I am not creating any extra array. So space complexity is not an issue. Time complexity is something that will be an issue. Okay. So first of all, why is it really an issue that it's taking extra time? Because things will be slow, right? And just to give you an estimate, if you're trying to participate in any online competition and you want to figure out what should be the time complexity of my solution, because now I have thought of a solution. How do I decide that do I need to think of a better solution or this might itself be the best solution, right? How do I know there exists a better solution? So generally one way to figure out if you need to find a better solution in case of an online competition will be to look at constraints, right? Generally we assume a computer does 10 to the power 8 operations in 1 second, right? It does 10 to the power 8 operations in 1 second. Generally we assume that. So most of these competitions will have a deadline of like a time limit of 1 to 2 seconds for each test case, most of the times. So if it has 1 to 2 seconds, that means you can do these many operations. You can do 10 to the power 8 operations. Okay. So if my problem is big O of n square, and if my solution is big O of n square and n is given to be of this constraint, let's say 10 to the power 6, n is given to me that it is less than 10 to the power 6. 10 to the power 6 would mean n square work is what my algorithm will have to do, 10 to the power 12 operations. We will not be able to do 10 to the power 12 operations in 1 second because in 1 second I can only do 10 to the power 8 operations. So it kind of tells me that n square is not good enough. I need to find a better solution. Right? I'm just giving you a small trick into figuring out that has nothing to do with this problem. In general, if you are taking part in any online competition, any competitive programming, then generally you would know what is the constraint given to you. And if the constraint is given to you, you can kind of guess till what time complexity your solution will be accepted. Here, if I had said 10 to the power 3, I would have been sure that n square will work fine. Right? N square is not going to be an issue. 10 to the power 6, I'll say n will work as well as n log n will work as well. Right? So that's where basically we can give some idea around if this is good enough or not. Okay, coming back to the problem that we have. This is the problem. We have to find intersection. Now you are doing mn work, and let's say if both of them are equal, then you are doing n square work, right? If they are almost in the same range, then you are doing n square work. Okay, what can we do now? So let's say I have this algorithm in which I am doing n square work. Okay, if I add some extra work which is taking n log n, what would be the total time complexity of my algorithm now? So previously it was doing n square work. Now I have added some extra work which is happening only once, and that work is taking n log n time. What is the total time complexity of my algorithm? So total work it has to do is something like k1 n square plus k2 n log n, and as you already know, this is something that we can ignore because degree of n is less here. We can just say it is k1 n square. So again the time complexity will still be n square. It will not be worse than n square. You are doing some additional work, but that has not changed the time complexity, because the work you are doing is still not is far less compared to the work you were doing already, right? What am I trying to say? What I'm trying to say is, if a problem is with respect to arrays and you are taking n square work, you are already doing n square work, then it's always worth a shot to sort the array first. Obviously this is a trick that this trick does not fit all array problems. A lot of array problems you will be able to get to better solutions if you use this trick, but not all of them for sure. So what I'm trying to tell you is, if you have an arrays related problem and you are taking n square time or more than n log n time, sorting is free. If you do sorting, your time complexity is not getting worse. But if you sort the array and you are able to decrease the rest of the work from n square to something else, your time complexity has improved. For example, let's say my original algorithm A was doing n square work, and now in B what I do is I do n log n work to sort, and after sorting I only have to do n work, right? It's possible, right? So previously I was doing n square work because the array was unsorted. Now if I have a sorted array that I can do in n log n, I am able to complete my work in n. So what will be the time complexity of B? So you are doing k1 n log n work. Sorting is n log n. I am assuming we are using merge sort or quick sort. We are not using bubble sort, insertion sort. So n log n is how much I need for sorting. So this much plus k2n. We will ignore this part because this is more important. That basically means B is big O of n log n, which is much better than big O of n square. So please try sorting, and a lot of array problems will be able to you'll be able to get to better solutions. Okay, so now use your mind, try to find better solutions for this particular problem, which basically says you have two unsorted arrays, you need to find their intersection. Okay, so please spend some time and try to think of good solutions for this problem. Thank you. Hi. So in this session, I want to discuss a little better solution for array intersection. right? So you have two arrays, and to find intersection we were using mn, and in case they are of equal size we are using n square time complexity, big O of n square. We wanted to improve it. So the idea we discussed last time was we can try and sort the array, and sorting is going to be free for us, right? We don't have to worry about it. It's not really free, but basically I am already doing n square work. If I do additional n log n work, the overall time complexity is not changing. Okay, so let's try to sort it. So as a first idea, I have two arrays. Let's sort both of them. Sort A, sort B. So here you are doing m log m work. Here you are doing n log n work. Now you have two sorted arrays and you have to find intersection of them. The problem is like completely different now. You have two sorted arrays and you have to find their intersection. Now as soon as somebody tells me that I have two sorted arrays, the first algorithm that comes to my mind is the merge algorithm that we wrote for merge sort. That's the first algorithm that comes to my mind. Can I use that to solve this as well? Actually I can. This can be solved using the same algorithm that we used to merge two sorted arrays. How? This is how we were doing it in that case. So you take I and j, you compare, you move the minimum one forward. So if this is smaller, we will move I forward. And while you keep doing this, let's say I have a 7 here and I have a 7 here as well, right? So let me take a little better representation. Let's say I have a 7 here and I have a 7 here as well. So if you use the same routine, the same merge algorithm here, what's going to happen is, if you reach one of these 7s first, right, let's say in array B I have reached 7, in array A I have not reached 7, I need to make sure that I get all the intersection points, right? That's what I need to print. Now what's going to happen is, when you compare this element with this element, what will move? I will move or J will move? I think I will move. The fact that we have not reached 7 and the array is sorted means this element is smaller than 7. Because this is smaller than 7, I is going to move and J is not going to move. J is going to stay here till the point this I reaches this 7. It's not going to move. Because everything before 7 is smaller than 7 or equal to 7. In that case, you have reached 7 in the first array as well. That basically means if I start in both the arrays and I move one, then I keep following the other one, and like I keep going that ways, for each intersection point there will be one moment when I'll reach the intersection point at the same moment. And that's where I can check that both the elements are same, so I can print that as the intersection point. Okay, so the code will look something like this. If a of I is less than bj, it's not going to be exactly this, I'm just giving you a hint. In this case ai is smaller, so I will do I is equals to I plus 1. Else if bj is less than ai, that means j is pointing to a smaller element, so j is equals to j plus 1. Else they are equal, so you can print your intersection point here. So you can print ai, and you have printed it, so now you can say I is equals to I plus 1 and j is equals to j plus 1. So just giving you an idea how the code will look like. Okay, so originally you were doing mn work, now you have to do m log m to sort the first one, n log n to sort the second one, and then you have two sorted arrays, you are using I and j, and you are traversing through them. For a constant amount of work you are able to move one of them, right? I'm just doing that if else check and I'm able to move either I or j. and at max I need to move I to the end and j to the end. That basically means I need to do m plus n work at max, and all of these need to be multiplied with some constant k1, k2, k3, k4. But if you will see, these two are irrelevant with respect to these. M log m is definitely going to be greater than m, so we can ignore this. N log n is going to be greater than this, so we can ignore that. I don't know if m is bigger or n is bigger, so I will have to say my time complexity is m log m plus n log n for this particular solution, which is better than this solution. Because for example, if they are almost equal, then you were doing n square work, now you will be doing n log n work if they are almost equal. So we started with this solution and we have reached this solution, which is much better, right? So we had this solution, now we are at n log n solution. We can actually do something a little better than this as well, right? Something a little better, not much, but a little better. So let's look at that solution as well. So I have these two arrays, and what was I doing in my original solution? I was picking the first element, linear search. Second element, linear search. The linear search was what that was killing me. That was taking so much time, right? If I don't want to do linear search here, what do I need to do? I want to apply binary search here. If I want to apply binary search here, I need to sort B. Don't sort A, just sort B. So if B is sorted, you can pick each of these elements and do binary search in the second array. So how much time will this algorithm take? So first of all, this is n size, this is m size. N log n to sort B plus you need to search these elements in this array. Searching one element in this array with binary search is going to be log n, that we have already seen. How many elements do you need to search? You need to search m elements in this array, so it's going to be this much, n log n plus m log n. So this is third algorithm that we could have used, which will give us a different time complexity. Okay. Why is this better than this? This is better than this because I can sort the array which is smaller. I will not sort B. I will not always sort B. I will sort the array which is smaller. So I can make sure that n is less than m. Right? So first of all, you get two arrays, you check. If array A is smaller than array B, then I will sort array A instead of sorting array B. If array B is smaller, I will sort array B instead of sorting array A. So I can make sure that this log n is less than log m. So I will see a little improvement compared to this algorithm will perform a little better, right? So in this, we were sorting both of them and then we were applying a technique similar to merge. In this, I'm just saying sort one of them, whichever is smaller, and then search all the elements of other array into this array, and you will be able to get to a better solution. Definitely both of them are better than the original solution that we had. So if you were not able to think of these solutions, please implement them now, and hopefully your code will be, you will be able to submit your code without a time limit exceeded problem. Okay, thank you. Hi, so now let's pick another problem and let's work on that. So the problem that I want to pick is called equilibrium index. So what is this problem? So we need to find an index I where there is an equilibrium in the array. That means the sum of elements on left should be equal to the sum of elements on right. So there is an equilibrium, right? Like it seems like there is a balance, like the sum of elements on left is equal to sum of elements on the right. So we need to find that index where this is happening. If it doesn't happen, then you can return -1. Okay, how do we go about doing this? So there is a good chance that like if you had asked me this problem, the first solution I would have thought of would be a very naive solution with a little bad time complexity. There is a good chance you have found the same solution because you were not equipped to find the time complexity so far. Now let's see, in case you have done something better, that's great. But let's look at one solution and see what is the time complexity of that, and let's try to find a better solution. Okay, so if you ask me that, hey, I'm giving you array, find equilibrium index. The most obvious approach will be, I'll go to each index one by one. For each index, I'll find sum of the left side, sum of the right side, and see if they are equal. If they are equal, this is my equilibrium index. Otherwise, I move to the next index, right? So what I'll do, what am I planning to do? I'm going to go to each index. When I reach a particular index, I will find the left sum, the right sum. If they are equal, I return that particular index. Otherwise, I'll move this to the next position, and now this becomes my left side and this becomes my right side. This is my equilibrium index option that I'm considering right now. I'll again find the left sum, I'll again find the right sum, and that's how I'm going to work, right? So what do you think is the time complexity for this? So what are you doing? You went to the first index, left sum was nothing, like you don't have to do much work for that. For right sum, you have to traverse the whole array. Okay, so in this case you had to do n work, some constant k into n work. You have to go through the complete array. In the next iteration, I'll come here. The left part is just one element, but the right side is n minus 2 elements. So here I could have said n minus 1, k into n minus 1, because I have to go through these n minus 1 elements, but just for easy calculation I'm going to call it kn. Kn minus 1 and kn are almost the same, doesn't matter. Here again you have to go through n minus 1 elements, one on left, rest on right, so you will again do this much work. In the next iteration you will find some of these two and some of these as the right sum, again kn work. So for each index you are doing kn work. How many indices are there? N indices. Wow, you're doing kn square work. The time complexity is big O of n square, right? So you're doing big O of n square work. That's a lot of work that you're doing to find equilibrium index. We need to find a better solution. Now if we try and use the trick from the previous problem that we discussed, that sort the array, and let's see if that helps. I don't think that's going to work here, because as soon as you sort the array, the original problem is gone. The equilibrium index here will not be same as the equilibrium index in the original array. They are completely different problems now. They will not have the same answer. So sorting the array is not going to be the right solution here. I think my problem is that I'm finding this sum again and again. I'm finding this right sum, and then I'm finding this right sum again. I just calculated this. I should be able to get this value some way, right? I should not have to go through all these elements again. Similarly, for left sum, I've calculated sum for this element. Now when I move it, I'm going through this part again. And then when I move it a little more, then I'm going through all this again. I should not have to do all this work again and again and again. I should be able to reuse some of the work for the next index that I'm exploring. Okay? Try to think about it. I hope you'll be able to find an answer to this, and then try to write code for that. Okay? Just try to think can we somehow reuse the information that we have to calculate the right sum next time? Or whatever left sum we know, can we use that information to find the left sum in the next iteration? Okay, perfect. Thank you. Hi. So now let's talk about what could be a good solution to the equilibrium index problem, right? So this is equilibrium index problem. You have this array, you want to find an index I where the left sum is equal to the right sum. So how do we do it, right? What we discussed earlier was go to each index, find the left sum, find the right sum, and the time complexity becomes order n square. Can we do something better? I think we can. Let's do one thing. So when we start here, right? Let's find the right sum one time. So let's find this right sum. So we know the right sum. We go through the complete array once. We know the right sum. Let's say this is sum 100. Okay. Now at this index, the left sum is 0 because there is nothing on left side. So you start here. Okay. Now your current index that you are exploring is 0. Now if you know the left and right sum for this index, then when you move to the next index, just update your left and right sum values. I think your right sum now should not include this element, right? It should not include this element. So we need to subtract some value from here. And your left sum should include this value. So we need to add this to the left sum. So this needs to be subtracted and this needs to be added. Okay. Let me repeat that. Let's say at some particular index, I have already calculated the right sum and the left sum. Once you complete your work for this particular index and let's say you realize they are not equal, the right sum is not equal to left sum, then when you move to I plus 1, I think the new right sum will be equal to the right sum that you had previously, this value, minus a of I plus 1. This element needs to be subtracted from right sum. And the new left sum will be equal to the previous left sum plus this needs to be added. This needs to be added. This needs to be added. So you are able to find left sum, the new left sum and the new right sum by changing a little bit in the previous values. You don't have to go through the array again. You are able to do some slight changes and you are able to find the new values. Okay? Perfect. So it seems like I need to find the right sum once. So I'll do some k1n work to find the right sum initially. And I'll go through each index and at each index I need to do some constant work, that's it. So some constant work at each index means this much work, the time complexity will be big O of n. Okay, it will be big O of n. Perfect. So let me quickly do one thing. Let me write the pseudo code for this so that you are able to implement this as well. Okay. So the way I am planning to do this is, instead of finding the right sum, I am going to maintain total sum. Let's say I know the total sum. So I'll go through the complete array and I know the total sum, whatever value it is. The left sum initially is 0. Now whenever I want to find right sum, let's say I am at index I and I know the left sum, I know the total sum, then I can just do total sum minus left sum minus a of I because left sum is this much. So I can subtract this as well. I'll get the right sum. So instead of maintaining both left and right, I'll only maintain left. So left sum will not be 0 here. It might be, but in general it will be sum of these elements, right? So while going, I'll keep maintaining the left sum, and whenever I want to find the right sum, I'll use this formula to find the right sum instead of maintaining both of them while I'm traversing my array. Okay, let's write some pseudocode for this. Okay, so initially total sum is 0. I will go through the length of my array, let's say A. I is 0 as well. I'll do total sum plus equal A of I is equals to I plus 1. So basically now you have total sum with you. Left sum, I am going to start with 0. Okay. Now I am going to traverse through this complete array to find my equilibrium index. The first index I am going to explore is going to be index is equals to 0. How much work I need to do? So I am continuing here. Let me get rid of these. Okay, so I'm going to continue here. So while index less than length of A, what am I going to do? I already know the left sum. For index is equals to 0, the left sum is correct. So I already know the left sum. I don't have to do anything about this. So ignore this. I'll find the right sum. And we already discussed what right sum will be. Total sum minus left sum minus A of index, the current index that I am at. So this is definitely going to work fine for index 0, right? At index 0, what is the right sum? Total sum minus left sum, which is 0, minus A of index, which is this element. So this will give me the right sum. Here, if right sum equal left sum, in that case what I am going to do is, if both of these sides are equal, I can simply return index. I'm done. I have to find the first equilibrium index. In case they are not equal, I need to change my left sum. I'm not going to change right sum. The next time I come inside the loop, I'll update my right sum using these three values. For now, I'm just going to update my left sum. So how to update left sum? So whatever was the left sum, that stays as it is. When you move from index to index plus 1, your left sum needs to have this value as well. Okay, so let me repeat that. So this was my left sum, this was my index. Now I am moving to index plus 1. So whatever was my left sum, I need to add this entry into that left sum to find the new left sum. So this will be A of index. So this is how I can update my left sum. Once you have done that, you can do index is equals to index plus 1 and you will be done. So in this code, if you see, what I'm trying to do is I'm maintaining the left sum as I'm going. And because I know the total sum, I'm able to find this answer. Okay. If this while loop gets over, that means you never found your equilibrium index. I went through all the indices, from nowhere I returned, that means I can return minus 1 eventually. Okay. If you look at this code, you have this loop, but within this loop, I'm doing constant work. So I'm doing kn work, that means my time complexity is big O of n. Okay. Let me quickly take an example and dry run this for you. Okay, so let's take this example. Okay, so now the way I'm saying is I'll find total sum. So that will be, I'll go through this array once. So 1 plus 3, 4, 8, 10, 12, 12 plus 5, 17, 17 plus 5, 22. So total sum is 22. First of all, this becomes my index, my left sum is 0, right? So I find the right sum. How do I find it? 22 minus 0 minus the current number. So I find the right sum to be 21. Are these two equal? No, they are not equal. So I want to move to the next element. While I'm doing that, what I'm trying to do is I'm updating my left sum. So left sum gets a of index added to it. So left sum instead of 0 becomes 1 now. When I come to 3, I find right sum again. How do I find right sum? Total sum minus left sum minus the current element. That means 18. Are they equal? No, they are not equal. So what do I do next? I update my left sum by updating the current with the entry that I am currently working on. So I add them, it becomes 4. Now here when you reach this index, you find your right sum again. How do you find it? Total sum minus left sum. So 18 minus the current element, 14. They are still not equal. And we'll keep moving like this. I'm just going to complete this, but what I want to show you is left sum is 4, right? You are finding left sum while you are moving. Now these two are not equal, so you update your left sum by whatever it is right now, which was 4, and adding the current number, it becomes 8. Now you come to the next number, you find your right sum again. How do you find right sum? Total sum minus left sum minus the current element, 12. Are these equal? They are not equal. So you update your left sum. How do you update your left sum? You add the current element in the existing left sum. So it becomes 10. Now you come to this index. When you come to this index, your right sum is total sum minus the left sum right now, which is 12. So 22 minus 10 is 12 minus the current element. So right sum becomes 10. As soon as that happens, your right sum is equal to left sum, so you return the index of this particular 2, and that's how your code is working. Okay, so you're maintaining left sum. As you're going, you calculate your right sum by doing a small calculation because you know the total sum, and you are able to check for each index by doing constant work. That's how our solution became big O of n. Okay, perfect. Please write code for this, and this is a much better solution than what we had earlier, which was order n square. So please implement this and please practice the assignment. Try to find good solution for all the problems that are added in the assignment. This assignment, I think, will have all the problems that you've done earlier as well. But this time we'll have to write better solutions for these problems. Okay? Thank you.
Hi. So in finding unique element in an array question, you will be given an array of size 2n plus 1. Now out of these 2n plus 1 elements, n elements will be duplicate and there is one element which is unique. So our task is to find out that unique element. Let's take an example. Let's say n is 3, so I'll have a total of 7 elements. Right, so 6, 1, 6, 3, 4, 3, 1. Suppose I have an array like this. So I have to find out the unique element. This is my task. So how should we actually proceed about solving this? I think the simplest approach that we can think about is, so in order to find whether an element is unique or is its duplicate, I have to go and look up for that element in the array. I'll go and look up for that element. So if I find another 6 in the array, that means it's duplicate, and if 6 is present only once in the array, it's unique, right? So let's go about solving this way. So pick an element, pick the first element or start with the first element, go look for the first element in the array. So in this case I'll find 6. So 6 is not unique, right? So move to the next element. Look for 1 in the complete array. So if 1 is also present, this is also not unique. Now you encounter another 6, go and look for 6 in the complete array obviously, and you find another 6, so that means 6 is also not unique. Same for 3 but not for 4. So 4 will be unique and we will be able to find that, right? So this is one simplest approach that we can definitely go about using to solve our problem. Okay, so now we need to discuss and figure out what will be the time complexity of this approach. This is the simplest approach, right? So our next step should be to figure out what is the time complexity. What do you think? What will be the time complexity? For every single element, you have to go and search in the complete element, in the complete array, that whether that element is present in the array or not, right? So you will be searching for n elements. For every one element you have to search for 2n plus 1, or rather n elements in the array, right? For the next element you will do this 2n plus 1 task again. That means for a total of 2n plus 1 elements you will do that. So if 2n plus 1 is size of array, time complexity of this approach will be size square, size into size, because for every element you have to do size work. So if there are total of size elements, the complexity will be order of size square. So this is one approach. Obviously the complexity this way is not very good, so we need to think of something different. Can we actually do it better? I think the next thing that we can do is we can think about how about sorting the complete array. Why not we sort the complete array? We'll be able to figure out that way, right? So if I sort the complete array 1 1 3 3 4 6 6, this will be the array, right? I just have to make a scan, right, and search for 1. If 1 is equal to the next element, then it is duplicate. Same for 3, 4, not for 4, so 4 is the answer. So if I sort the complete array and do it, I think this will still turn out to be a better approach. So sorting will take n log n, or I should say size log size here. Total of size elements. So sorting will take size log size. One more scan to check for the unique element, so that will take s time at max. So the total overall time complexity of this approach will be s log s. So this is another approach. I think we can even do better than s log s even. What can we do? So I hope you guys are aware about the XOR operator. In case you are not, I'm sure you must have read about gates, AND gates, OR gate and XOR gates as well. XOR is a bitwise operator. That means it operates at bit level. So for example, let's say I have a number 6. The bitwise representation of 6 is something like this. Another number 5. Bitwise representation of 5 will be this. So you have to calculate XOR of 6 and 5. Then it will work at bit level. If 2 bits are equal, their XOR is 0. If they are not, their XOR is 1. So here 2, 0 and 1 are unequal. 1, 1, 0, 1, 1, 1, 0. So XOR of 6 and 5 basically is 3. So this is XOR. So, right? How do you write it? If you have to calculate XOR of two variables, symbol uses this. A XOR B. This is how you find out XOR of two elements. Right? So how can XOR fit in here? XOR has an amazing property. So for any number, A XOR A will turn out to be 0. That means obviously 6 XOR 6. Obviously, two consecutive bits will be equal, right? 0 0 equal, 1 1 equal, 1 1 equal. So answer is 0. So A XOR A turns out to be 0. And we will use this property in our solution. How are we going to proceed? I will calculate XOR of all the elements in the array. One by one, travel to every element and calculate their XOR. That means you are going to calculate 6 XOR 1, XOR 6, XOR 3, XOR 4, XOR 3, XOR 1. Right? XOR is also associative. Right? I hope you remember associative property. So that means 6 XOR 1 XOR 6. I can write it as 6 XOR 6 XOR 1. I can reshuffle that. So 6 XOR 6 will be 0, right? Similarly 3 and 3, 3 XOR 3 will turn out to be 0, 1 XOR 1 will turn out to XOR 6 XOR 1. I can reshuffle that. So 6 XOR 6 will be 0, right? Similarly 3 and 3, 3 XOR 3 will turn out to be 0, 1 XOR 1 will turn out to be 0, and there will be 4. So ultimately we will be calculating 0 XOR 4, 0 XOR 4 is 4. So answer will be the unique element. We can use XOR here. That means if you calculate XOR of all the elements in the array, so the remaining result, the remaining number that you will get will be the unique number. So you can do that. Now this is our approach. We need to find out the time complexity. How much time do you think will this approach take? What you have to do in order to find out the unique element? You just have to scan the complete array and calculate the XOR. So if the complete array is of size S, this approach will take order S time. So we are able to find out the unique element in order of S, which is really amazing. So this is, I think, the best approach out of 3 that we have discussed. You can again think of 3 approaches, try implementing them. Obviously we will work over the best approach because that will give us decent results, but yes, we should understand how have we evolved from the S square approach to an S approach. Okay, thank you. Hi, in duplicate in an array question, you will be given an array of size n which contains elements from 0 to n minus 2. So numbers from 0 to n minus 1, that means these are total of n minus 1 unique numbers. So out of these n minus 1 unique numbers, there will be one number which is duplicate, and our task is to find out that duplicate number. So let's understand with the help of an example. Let's say n is 6. So if n is 6, that means numbers will be from 0 to 4. So total of 6 elements, 1, 2, 3, 4, 5, numbered from 0 to 4, 2, 1, 0, 4, 3, let's say. So out of these, there will be one number which is duplicate. The duplicate number can be at any place obviously. So there is one number which is duplicate, let's say 1. So 1 is the duplicate number. Now our task is to find out this duplicate number. So there are multiple ways which we can solve this problem. So the first and simplest approach is, let's go and search for the number in the complete array, right? So if I find it again, so it is redundant. If no, then it is okay. We should move on to the next number. So that means start with 2, right? Pick 2. Go and search for 2 in the complete array. So we will not find 2, right? 2 occurs only once here, so it's okay. So move to the next number, go look for 1. 1 is redundant, so you will find 1 twice, right? So what will be the worst case time complexity of this approach? What will be the worst case time complexity? So every number we are doing n work, that means comparing and figuring out whether it is present in the array or not, right? So okay, so for the first number, you will have to go and look for all n minus 1 numbers. For the second number, you will have to go and look for next n minus 2 numbers. For the third number, next n minus 3 and till 1, right? This is the task that we'll be doing. So this turns out to be sum of first n natural numbers, n minus 1 natural numbers I should say. So order of n square. So the complexity is order of n square, and by n I mean n is the size of the array, right? So order of n square is the time complexity of this approach, which is the simplest of all that we have discussed. So now let's think and figure out if we can do better. Yes, we can. Why not sort the complete array? So let's do one thing, sort the complete array. So if I have to sort the complete array, then 0, 1, 1, 2, 3, 4. This will be the array, right? So check if 0 and 1 are equal. No, they are not. 1 and 1 are equal. Yes, they are. So that means 1 is the duplicate number. This way you can find out the duplicate number. So if I go by this, what will be the time complexity? I think the time complexity of this approach is, first you have to sort. So sorting will take n log n. And then you have to scan. So one scan of the complete array will take order of n time. So dominating term out of these two is n log n. So I'll say the complexity of this approach is order of n log n. Sorting and then figuring out. We can obviously take a step better and think of an algorithm which is better than n log n even. So how can we do that? What should we think? I think we have a huge information that the values of the array elements will be from 0 to n minus 1. That means the values range from 0 to n minus 1. Let's do one thing. Let's find out sum of all elements in the array. So sum of all elements in the array is 2 plus 1 plus 0 plus 4 plus 3 plus 1, right? This is what the sum is. So if you add, this will be 3 plus 4 plus 3 plus 1, that means 11. Sum of all elements in the array is this. Now, we know elements range from 0 to n minus 2. Why not find sum of first n minus 2 natural numbers? So n is 6, sum of first n minus 2 natural numbers will be n minus 2 into n minus 1 by 2, right? So 4 into 5 by 2, which will be 10. Sum of first n minus 2 natural numbers is 10. Now in this sum, only one number in the initial sum, only one number is duplicate. That means if I exclude the duplicate number, it is effectively sum of first n minus 2 natural numbers plus the duplicate number, right? So if I have to find out the duplicate number, why not subtract these two? Subtract the sum of first n minus 2 natural numbers from the array sum that we have, and the result will be obviously the duplicate number, because that's the only number which is added twice. So that will add to the initial sum. So this way we will be able to find out. Okay. So next step is to, obviously after we are done with the approach, is to figure out its time complexity. What will be the time complexity? So you have to find out the sum, array sum. You have to scan every element of the array and calculate its sum, right? So that will be order of n. Finding sum of n minus 2 natural numbers is just a formula. It will not take much time. Subtracting these two integers is also constant. So time complexity of this approach is order of n. So the best solution exists in order of n this way. I am sure there are multiple other ways in which you can do that. You must have thought of different ways doing that. So one thing that you should be careful about is, whenever you come up with an approach, please try figuring out its time complexity and space complexity as well. So if we discuss space complexity of the final solution that we have, space complexity will be order of 1. Time complexity will be order of n, which is an efficient solution. So whatever solution you have come up with, please spend time thinking about the time and space complexity of that solution as well. Okay, thank you. Let's discuss pair sum question. So you are given an array. In the array you need to find out pairs that sum to a particular number x. So let's say the array that we have is something like this, and the x that we are searching for is 0. So in this array now we need to find out all pairs that sum to 0. Okay. So how should we start about it? I think the first thought that comes to the mind is, let's pick 6. Search whether the corresponding number which pairs up with 6 to get 0 is present in the array or not. So that means if the number is 6 and I need to find out the numbers that sum to 0, then I should look up for 0 minus 6 in the remaining array, right? Search for 0 minus 6, that is minus 6 in the array. If minus 6 is present, then we have a pair, and repeat the process for every number in the array. Right, so same for minus 8, look for 8 if 8 is there or not. For 4, look for minus 4 if it is there or not. For 1, minus 1, and so on. Right, that means for every element you are looking for all other elements. Right, so that means for the first element I have to search for n minus 1 elements, right, in this array, whether there is minus 6 or not. And if minus 6 occurs multiple times, then there are multiple pairs obviously. For next number I have to look for n minus 2 numbers from that number onwards, for next n minus 3, and so on till last. Obviously this complexity will turn out to be order of n square. Right. So this approach that we have discussed is the simplest approach, and the complexity of this approach will be order of n square. Now the next step that we have to think is, can we do better than n square? And the answer obviously is yes, we can do. So whenever you are given a question of unsorted array, one thought that you should give is whether sorting will help us or not. So let's figure that out. Sort the array. So if I sort the array, then the result will be minus 8, minus 6, right, minus 4, and 1, 2, 4, 6, and 15, right. So total of 8 elements. So this is the sorted array. Now as soon as I sort the array, that means n log n is the time that I've already spent in sorting the array, right. So I've already done that. N log n is the time. Now how should we proceed further? Let's first try adding the smallest element and the largest element. So the smallest element of the array will be the first element now, since the array is sorted, and the largest element of the array will be at the last, right. So I at 0, j at the last. Okay. Add the numbers, add the elements at I and j. So minus 8 plus 15 comes up to be 7, right. Now the sum that I was looking for is 0. The sum that I have got is 7. So 7 is greater than the expected number, right. That means I have added a bigger number. I have added a large number, right, which makes the total sum to be greater than the required sum. So what I should do is try adding number which is just smaller than 15. So that means decrease j by 1, and now try adding minus 8 plus 6. So minus 8 plus 6 comes out to be minus 2. Expected sum is 0. I am getting minus 2, which is obviously lower than what I expect. That means the negative portion is greater than the positive portion, right. That means I have added a number which is smaller, and I should try adding a number just greater than minus 8. So increase I. Now try adding the elements at I and j. The sum of elements at I and j is 0. Perfect. So I have one pair with me. Print the pair. Move ahead. Minus 4 plus 4 also comes up to be 0. I have another pair, right. Move ahead. 1 and 2, right. The sum is 3. Expected sum is 0. That means I have added a bigger number. I should reduce j. But now I and j point to the same element. That means I cannot find any more pair further. So I should stop. So I should repeat this process of adding the element at I and j till I is obviously less than j. Till there are a certain number of elements in the range of I and j. And whenever you find an element, whenever you find a pair, you should print that pair and proceed. I hope the approach is somewhat clear to you. So what are we doing? I had taking two variables I and j, both are moving at their own pace, right, depending on the variable, depending on the sum. So the maximum time that this approach can take is order of n. So n log n already we had spent because we were supposed to sort the array, and now after the array is sorted, in order to find pairs, I'll take n time. So I hope the idea is clear, but let's spend more time in this approach. So let's take a different example now. Let's say the elements that I have are 1, 3, 3, 4, 5, 8 and 9, 9, 9 and 15. Suppose these are the numbers that I have. Now I have to find out pairs that sum to 12. So all the pairs that sum to 12, this is my target. So start with I and j, right? Find out the sum of elements at I and j. Sum is 16. I need 12. So obviously the larger component is there. So I should try adding the number which is just smaller. 1 plus 9 is 10. I need 12. So pairs that sum to 12. I should try adding the number which is just greater than 1 at least. Just greater than 1. So add 3. 9 plus 3 is 12, right? So print the pair. If I move both I and j further, in this way I get only 2 pairs. But in the question, as per the question, if we have read it, there are total of 6 pairs of 3 and 9. So this 3 will pair up with these 3 9s. Second 3 will also pair up with these 3 9s. So in this case, what you should do is, rather than just moving I and j further, you should count how many 3s are there. You should count how many 9s are there. If there are 2 3s and 3 9s, total of 6 pairs will be there, and you should print all of them. So you should print all the pairs. So printing all those pairs, and then you should move ahead. So then take step further, add I elements at I and j, they also sum up to 12, print another pair, move further. So this is what you are supposed to do, right? So this is what your target is. Now there can be another interesting case which you have to think about. So let's say I have an array like this, all 2's, and I need to find out pairs that sum to 4, right? So I and j. If you follow by our approach, right? Now counting i's, counting j's can be misleading here. So in this case, how many pairs will have? This 2 will pair up with 4 2's, second 2 will pair up with 3 more 2's, this 2 will pair up with 2 more 2's and 1. So total number of pairs in this case is 10. So you should be careful around that. So please take care that you handle this case as well. So this is also important, and cases which have duplicates as well, because had there been only unique elements, the approach that we discussed just before this would have been okay. I, j, take I further and do that. In case of duplicates, you will have to be little more careful about dealing with the pairs and their count. Okay. So about the complexity, n log n was the complexity that we spent on sorting. It depends on the sorting algorithm you are using. I definitely hope that you will be using an efficient sorting algorithm. So it will be n log n for sorting. So had our task been only to count pairs, it would have been order of n for sure. But if I have to print all pairs as well, then it is not n always. For example, in this case, what is n? N is 5, right? But I have to print first n minus 1 natural. So I have to print total 10 pairs. So the time taken will be corresponding to this 10. So it can be n square depending on number of pairs that you have. If you have n square pairs, there is nothing better that you can do, because in this case I have n square pairs, or I should say n minus 1 into n by 2. This is the pair count, right? So if I have n square pairs, then I cannot improve that. I will have to print all of them. But had my task only been to count the number of pairs, then I would have surely achieved it in order of n. I hope the idea is clear, the approach is clear, and now you can code. Thank you. Hello. So the question that we are going to discuss is, you are given an array and you need to rotate that array by d positions. So let's take an example. Let's say the array that I have is 2, 6, 3, 1, 5, 9 and 8. Suppose I have an array like this and I need to rotate this array by d positions. So let's say d is 2. So I have to rotate this array. Expected output, so I'll write it here. So the output that you will expect is finally, so let's perform rotation one by one. So if I rotate by 1, right, so if I perform the first rotation, after first rotation every element will shift by 1 towards left. So after first rotation it will be 6, 3, 1, 5, 9, 8 and 2. After second rotation, this array will be 3, 1, 5, 9, 8, 2 and 6. And this will be our answer. This is our target. So this is what we are supposed to do. D is the number which will be given to us, and we need to rotate the complete array by d positions towards left. So this is what our target is. So let's now discuss how can we actually go about solving this problem. I think the first and simple approach can be, let's perform d shifts in total, d complete shifts of array, and one shift obviously one at a time. So if I have to shift this array by just one, let's discuss. If I have to shift this array by just one, what am I going to do? These are the indices of the elements. Okay. These are different array indices. So if I have to shift by one, element at index 1 will go to index 0, element at index 2 will go to index 1, index 3 to 2, 4 to 3, 5, 6. Right? What about the element at 0th index? Element at 0th index will go to the last, will go at the last. So if I have to shift this array by 1, what I should do is first store element at 0th index in a temporary. Shift all elements from index 1 to end. Shift all elements from index 1 to n by 1, and then at the last index place this temp. So place this temporary at the last index. To shift, obviously index 1 element should go to index 0, right? Index 2 element should go to index 1. So for every I element at index I plus 1 should go to index I. So I plus 1 just next day should go at index I, and so on. So we should do it. So this whole shifting step we need to do total d times. So this was the task that we discussed. To shift array by 1, we have to shift array in total by d. So we should perform this task repeatedly total d times. Okay, I hope you can visualize how the code is going to look like. How are we going to proceed? So this is one way of solving it. Okay, now let's discuss another way. Why are we discussing another way? I think this will definitely solve our problem, but we are doing a lot of work here. So we are performing total d shifts. Every shift will actually move every element of array by 1. So in all that's quite a lot of work. Can we actually do better? So let's discuss that. What's the array? 2, 6, 3, 1, 5, 9, 8. So 2, 6, 3, 1, 5, 9, 8. This is the array that we are talking about. Okay, so I have to perform d shifts. D is 2. So finally after d shifts, array will be 3, 1, 5, 9, 8, 2 and 6, right? So ultimately every element will be displaced from its current position by d positions. That means index 0, 1, 2, 3, 4, 5, 6. These are the elements. So the element at index 2 will go to index 0, element at index 3 will go to 1, 4 will go to 2, right? So every element will ultimately shift by d positions. That was something we were actually doing in the previous case as well. So that means if I have to shift every element by d positions, I can simply do this. Element which is currently at index I plus d will shift towards left and come at position I, right? For all elements from position d to end, for all elements from position d to end, from position 2 to 6, they will be displaced by 2 positions towards the left. What about first d elements? If I'll directly place element at index 3 at index 0, we will lose the element at index 0. So we cannot directly shift. Before doing this actual shift, we should store first d elements somewhere. And in order to store first d elements, let's keep an extra array. So where I'll first of size d, I just need this array to be of size d. Let's store first d elements here, then perform this shift by d positions, and then copy back these d elements to at the end. So at the last d positions, let's copy back these d elements at the end. So I think we can achieve this. So what I'm talking about is shift all the elements 3 by 1, 1 by 1, 5 by 1, 3 by 2, 1 by 2, 5 by 2 positions, and so last d positions will be like this. Let's copy back first d elements here. So we will achieve our target. We'll achieve our target this way. Okay. This is relatively better obviously than the first approach that we were discussing, because the first approach that we discussed will actually take lot more work to be done in order to perform the shift. Here we are shifting every element by d, right? Taking an extra array to store first d elements and then keeping them back. So this is the second approach in which we can do it. I think there is another approach with which we can solve it. So let's discuss that as well. 2, 6, 3, 1, 5, 9, 8. Zero, 1, 2, 3, 4, 5 and 6, right? So this is put target if d is 2, 3, 1, 3159,826. 3159,826. Right? This is what our target is. So let's do one thing. We have this array. This is our answer. Let's reverse this array. We know how to reverse an array, so let's reverse this array. So if I'll reverse this array, 8 and 2 swapped, 9 and 6 swapped, 5 and 3 and 1. I'll have an array like this. Target is something like this. Are we close to our target? Not exactly. But what we can do is, let's reverse these n minus d elements and rest reverse these d elements again. So if I reverse them again, if I reverse only these d elements amongst themselves, then I'll have this as 2, 6. 2, 6 is what I desire for last d elements. If I reverse first n minus d elements, 8, 1, 9 and 5, I'll be done. So this way we can achieve it. What you can do is, this way what are we doing? Reverse the complete array, reverse first n minus d elements amongst themselves, reverse last d elements among themselves, and you will achieve this. Okay. I hope all three ways are clear to you. So second way that we did was take an extra array, shift every element by d positions. The first way that we did was perform one shift total d times. So all these three logics are clear. You can try and obviously start with any one approach that you feel comfortable with. I would recommend that you should try and code all three approaches yourself, so that way you will get clarity. How can we approach solving a problem by multiple techniques? So we can do that. Okay, I hope this is clear, and now you are good to go. Thank you.